Hi. So, let us welcome back to the lectures on GPU architectures and programming. So, if you remember in the last lecture we have stopped midway in the kernel and buffer object creation commands that are available in OpenCL. Now, so once we have got those definitions in place, so let us actually use them to create the read write buffers in which we can store a read from and write to for the OpenCL kernels, right. So, this is how we will be creating a CL memory object, right. So, you have a data. So, suppose you are creating the input arrays in the device memory, where you will transfer data from the host program, OpenCL host program. So, you execute the command CL create buffer in that context, right, and for the device, and what you do is you have to specify the operation type. So, this is specified that it can either do a CL mem read only or it CL mem copy host PTR. So, these flags, so these memory flags actually tell that what are the operations that are allowed in the buffer, like it is allowed to copy data from the host side, right. So, with that you are creating these two OpenCL memory objects DA and DB using the CL create buffer command inside the context, right. So, the buffers are created inside the context, they would be usable by the devices in the context, right. You also create the output buffer, right, where the system would be writing the output. As you can see that again you create the CL create buffer in the same context, but the memory flag is set as CL mem read write, right, because now for this you also want the device side code to write its output. The OpenCL kernel should write its output here, and the size of the buffer is given by this data size parameter using, as you can see that size underscore t type argument is there here, right, and of course, you have to provide the host pointers, right, that they are going to get information from which host side code. Now, which host side memory objects, like if you remember, so just to recall things, we have got this host side arrays, right, HA, HB and HC defined. So, the HA and HB are containing the input arguments, and HC we plan to write back the data after their computation in the device side OpenCL code. So, here you have also specified that what are the operations to be done, and they are to be related with which host side data structures HA, HB and all that, and then in this context you have also created the buffer where you want the output back, that is DC. So, now the other thing that we will do is you want to pass arguments for the kernel. So, if you remember you have the vector at kernel there available with you, right, and this is the kernel object that we have created with the build kernel commands earlier that we have discussed. Now, for this kernel object we are creating this argument list by calling this function as many times as are the number of arguments. So, you want this to be provided with the two input buffer pointers, the output buffer pointer and the number of elements bound, right. So, that is why you have 4 arguments and you have these multiple calls. Now, the issue is why do we have multiple calls? It may happen that in each of these ideas, each of these initiatives of trying to provide arguments to this kernel, you face an error, right. So, for each of those operations you can have separate calls here, so that in case you get errors in any one of them, it will be flagged out here. So, I can write some handler code out of this, that if in any of these operations I get an error, I do an OR of this, then you exit from here. Now, the issue is I want the kernel to work, but like a normal data parallel program, as we have seen, that I need to pass it the work dimensions of the kernel. What is the global work size and what is the local work size for this kernel, right. So, for this we have to identify, still now whatever we have done is we have identified platforms or devices, but we need to identify what is the dimension the kernel's execution that a device can support. Now, as you can see that this is something again which is very generic in OpenCL specific, like inside a device I can have support for a multidimensional kernel, and up to what dimension specification of multidimensional kernel is allowed for the device may be device specific, right. So, the first we need to figure out what is the maximum work item dimension that is allowed in the specific device. Again, I am just saying that just for a vector addition this is not necessary. We are trying to give you as much information, system level information possible through this kind of code, right. So, for that we have this count variable which is storing the length of the inputs on which you want to work. Now, here is the important function that we will be using, CL get device info. This is going to give back some CL type integers, and you are passing it some device ID, OpenCL device ID, right, and you are passing it some parameter which you want to query, that what is the parameter you want to query, right, and then you would expect some values to be returned by this function, and let us see the function working to get some more idea. So, you have also defined another integer here, unsigned integer, which you wanted to store the maximum work item dimension which is supported by the device, right. So, if you remember, just a brief recall, in CUDA you had grids and thread blocks, I mean grid containing thread blocks, right. Here you have a global work size, and inside that you have work groups. Inside the work group you can have multidimensional arrangement of work items. You want to figure out in a given device what is the maximum dimensional specification that is allowed for a for that device, right. So, for figuring that out, you have the max work item dimensions. You make a call to CL get device info for the specific device ID. You pass it this instruction that hey, you have to return with the maximum work item dimension you support. So, you give this flag here, CL device max work item dimensions, and you want that value to be returned, right. And so, of course, the other thing you would do is you provide here a size specification of the parameter value, and that would be of type so you have a size T specification here, right, which is like the size of what is the size of uint, right, unsigned integer of type OpenCL. So, here you are calculating that size by size of operations in C, and that gives you a value of type size underscore T, and that is something you are passing here because you want the parameter value size to be known, right, that in what form the function will give you back the parameter value size, right, because that is also something that may be device specific, right. And so, once that is given, you are also passing it a pointer here which is going to store that value. Now, observe the thing, this pointer is for data of type CL uint, right. So, you have to pass the pointer here, and you have to also pass the size of the data type for which the pointer will be initialized, right. So, this is a plain and simple, this is the unsigned integer type pointer. You want to give this to this is a low level get device info is a quite low level function. It needs to know from the runtime that okay, when I return back some value, what should be the maximum allowed length for the value, right. So, since it is real type unsigned int, I calculate using size of what is the number of bits allowed for that, right. So, that I can get to know in what size I will return back the value, right. And the last parameter returns null for this call. We will see it working later on. So, with this call, what we get is the maximum work item dimension parameter initialized, like this for this device, this is the maximum dimension that is allowed, right. Now, once the dimension information is provided to you, what you do is you create you are just creating a pointer here, max local size, and you are mallocing it with dynamically of each location size of size underscore T. And what do you really want to understand that okay, in each dimension first of all, I have already figured out what is the maximum work item dimension. What is the next information I would like to know? I would like to know in each dimension what is the maximum value that is allowed, right? Like the work items. So suppose the work item dimension is 3. So we know that I can have work items packed with entities of x, y, and z dimensions, right? Or let's say 0, 1, 2, 0, 1, and 2 dimensions, right? Now I want to know what is the maximum value I can have in this dimension, what is the maximum value I can have in this dimension, maximum value I can have in this dimension. To know that, I create this max local size array, and the important thing is for this array how many positions do I need for storage. I would need these many positions, each of size underscore t, and finally it will return back a pointer pointing to this type of again size underscore t, of course. So that is the typecast here, and for the malloc call you are now providing it the parameters that hey, you give me an array containing space enough to hold data of this type and for these many dimensions, right. So with this, since let us say I am coming back to the example, if the max dimension is 3, essentially I am going to initialize an array which can store 3 values, right, and that is what this call is doing, right. Why do we want to do that? Because again, so you can see the pattern here. Again I am going to make a call to CL get device info for the device ID, but now I provide it with a different parameter. Earlier I queried it with max work item dimension, now I am querying it with maximum work item sizes. Of course, the implicit thing is in each dimension. That is why now the return will not be to a single pointer, but now the return to be an array, right. It's not the return value was not returned through a single pointer earlier to a single position. Now it has to be a set of values that is to be written. So that's why the return type has now changed. As you can see, you are expecting this thing to be filled up. This max local size, you are expecting this to be filled up, right. So earlier it gave you back this parameter value size. Now you are expecting it to so earlier you gave it it just gave you the maximum dimension. Now you have given it an array for storing the maximum dimensions in each of the maximum values possible in each of the dimensions, right. So for that you have max local size which has been initialized and passed here, right, and here you have given it the size of this array. Of course, since the C type function, right. So you just don't give the pointer here, you also give it the maximum size, right, which you already know by the way from the max work item dimension multiplied by the size of the size underscore t data type, right. So with this you expect that the runtime system will now contain in different positions of max log size 0, max log size 1, and max log size 2. Like that, it will contain the maximum value of the local thread IDs in each of those dimensions, right. So once this is known, you will like to figure out your global works. You will like to figure out what is your local work size and all that. So of course, the global work size is count because that many values are there to be operated one, right. Now how is your local work size? All you simply want to do is you have to just identify what are the maximum work item dimensions in each of the in each of the work item dimensions, what is the maximum value which is already stored in different arguments of this array, and you just loop over the array and multiply the values to get the local work size, right. So once this is done, that is you have the local work size figured out, the next thing is you are going to write input data to the device from the host. Now the real game of executing the kernel would begin, right. So for that you have to start, you have to again you understand that in OpenCL everything is through the command queues. You give commands to the, you enqueue commands to the command queues. Those commands are going to be executed by the runtime system, right. So you have to enqueue commands for reads and write. The first thing would be that you want to enqueue the host side values to the device side buffers, right, in the context that you have set up. So, in your context you have the command queue commands that you have already set up. In this command queue you are enqueuing read buffer commands to read from the host side array HA to the buffers that you have defined inside your context, which are DA, right. So, just going back, these were your declarations of buffers, right, memory objects inside your context of execution, right, and they have already been told that, I mean, what are the host pointers from which they are going to read, right. Now, you just enqueue the read operations here, right. So, you enqueue read operations for the two arrays DA and DB. Once this is done, the next thing would be that you have to execute the kernel, right. So, again you have to enqueue the execution command for the kernel using cl enqueue ndrange kernel. That is the you are enqueuing this execution command in the command queue for the kernel KOVAD, that is the kernel object we have created earlier, and now you provide it with the global and local work size. Global work size was already known. We needed the generic code to figure out what is the local work size allowed for this device, right, because things in it can vary across devices. So, in this case, for this dynamic, using this dynamic piece of code, we have figured out what is the work item dimension, and then we have figured out in each of the dimensions what is the maximum work item size. We have multiplied them to get the local work size, right. So, we have provided these global and local work sizes, and now the kernel, we expect the kernel execution command to be executed by from the command queue to be launched to the device and getting executed, right. So, this global work size and local work size, they point to an array of work dim unsigned values that describe the number of work items in the work dimension that will execute in the kernel function. We will see examples of this. So, next comes the some idea about the work pool. So, essentially, or the work group that you have. So, in OpenCL, when you have launched the kernel now with the global and local work size information, the work groups associated with the kernel instance are placed into a logical pool of ready to execute work groups called work pool, right. Again, I will just repeat one thing, just in case you are wondering why we did all these things to figure out the local work size. Essentially, we figured out what is the maximum number of, what is the maximum work group size that is supported by the device. If we pass it here, then we are expecting that the devices will execute very efficiently. It will pack as many threads as possible in the local work groups and execute them, right. So, that gives you the most efficient execution. So, this work pool is essentially the ready to execute work groups. Of course, you have to understand that just like in CUDA, you can launch multiple thread blocks. Different thread blocks can be at any given time point in different states of execution. Like that, in OpenCL, you have work groups associated with the kernel instance, and you are essentially creating a logical pool of ready to execute work groups, and they are called work pools, right. Now, OpenCL does not constrain the order on how work groups are scheduled for execution in the actual device from the work pool. So, that is just like CUDA, you leave it to the onboard scheduler and runtime system to manage this execution of work pools. So, once in the work pool, you have independent execution of work groups which can happen in any order, and they can interleave among each other. So, some work pool will execute up to some point, and then maybe they are waiting for some long latency operation to complete, and by that time some other work pool can be launched and they can be executed, and so on and so forth. For each device, there can be only one work pool used by all command queues associated with that device. So, now this is important. For each device in the OpenCL runtime system, you can have only one work pool which is used by all the command queues associated with the device. There cannot be more than that many that work. I mean, you can have multiple work pools which are used by these command queues which are associated there. So, now let us come back to the execution of the host program that we are discussing. So, once we have deranged that kernel. So now we are so that kernel, after its execution, we would like it to be to read back the values that have been actually written by the kernel, right. So something we are expecting that the kernel is going to read the specification of this kernel is that is going to read its input arguments, because we have, if you remember, we have already provided it the arguments, right. So it knows what are its what is the locations from where it's going to read, and of course by the definition of the kernel it is going to write back in the DC memory buffer. So at this point we know that after the kernel's execution, if we are including a read buffer command, so once the kernel execution completes, I can get the data in DC, transfer it back to HC. So that read buffer command is now enqueued in the command queue, right. So again you see that read command is also, you don't directly read, you enqueue the read command in the command queue, right. You have some small test code here for testing whether the values are really correct or not after the communication execution in the OpenCL runtime. So you can, so this is something as simple host side code, it will execute in the host side, and you can just compare whether the HC values that have been computed by the device side code, they comply with the host side additions. Now once this is done, as we can see that in you have, you are done with your main computation. So before leaving the system, you would like to free all the objects that you have created. So you have cl release mem object command to actually release all the memory objects. You have cl release program to release the program object, and you can also release the kernel object. You can release the command queue, and finally, so this has to be done in this sequence, right. You remove memory objects, then you remove program object, you remove kernel. Once these are done and the command queue is also released, then you remove the final context, you release the final context, right. And also you release the host side arrays HB, HC, the system becomes free from all the defined and allocated data, and then you return back gracefully from the code. So as you can see that this is a quite complex OpenCL host code, but again I will repeat, the complexity primarily comes from the way we are viewing a complex architecture by in itself first of all, right. Assuming that the architecture is complex, we have to execute a lot of commands to create the context of execution. We can select which are the devices from different vendors that I can pack in the context and all that, but we have to understand that most of this code is is going to be fixed if you are going to use that same device, same platform, same GPU or same CPU for programming with some other execution, right. You just need to change the maybe your definitions of buffers, your definition of kernel and all that, setting of platform, setting of context, and everything can remain same. Unless, and also if you are going to use that device again, maybe you don't even need to change the command queue and all those definitions, right. So the point I am trying to make is most of the code for the host side is going to remain same. If you are going to write another functionality, write another set of kernels or orchestrate the execution of another set of kernels in the same platform device command queue, right. So most of the code is going to be same. As a developer, only thing you need to do is modify the other parts of the code. So that brings the question of this CUDA versus OpenCL issue. With all these things, then why do OpenCL at all? Well, let's remember that CUDA programs will execute only on your NVIDIA type CPUs, but OpenCL code will execute in any system where your devices are compliant with the Khronos specified OpenCL specification, right. It can be a collection of CPUs, even it can be NVIDIA GPUs, it can be AMD GPUs, and Intel CPUs, AMD CPUs, somebody else's devices, some other accelerators which support all these OpenCL specification and all that. And as we know that Xilinx based FPGAs also support OpenCL, so it can be a heterogeneous system comprising multiple such devices. So that's the advantage. So you don't get specific to one vendor, but that also makes it much more system level programming. Of course, if you are using OpenCL bindings like the C++ extensions or the PY OpenCL, the Python extensions of OpenCL, then Maybe in your program all these low level details you don't need to do, you can write a much simpler OpenCL program. With this we have the specification of the host program given here at the lowest level, that is a vanilla C level OpenCL program, just to provide you with the more intricate device specific details of an actual OpenCL program's execution. So, coming to a nice summary that we would like to make here. So, what really is the runtime systems overview? What are the different phases that you have gone through? So, we are trying to show a simple example here. You have a CPU and GPU. These are the two devices. Let us say you have married them inside a context. We know how to do it now. You have these programs, the program sources, right? The kernel sources, and you can have from the kernel source, you can compile them to create CPU binaries, you can compile them to create GPU binaries using suitable different compilation systems, or you can actually use our methods to create programs from the sources, right? And then you can actually use our methods from using the program objects to create the kernel objects, right? Then so that is a sequence, right? You have the sources, from them you can create program objects, from them you can create kernel objects, then you parameterize the kernel with the different arguments here, right? So, using the set kernel argument comments, you can specify the memory objects that are to be. So, all these things go inside the context of execution, right? This context means everything is here. Every execution orchestration will be happening inside this abstraction. Why do we, again we will repeat, why do we define this abstraction? Technically we are viewing a more complex system, there can be other CPUs, GPUs encapsulated inside another context type object, right? To bring in this abstraction we can have multiple contexts. So, inside this context we can have program objects, kernel objects, and we can also have memory type objects. Of course, they are required. So, that would be normal memory buffers. OpenCL also provides internal support for image type memory objects which are already there. So, with this you have the data read write parts ready, where from to read, what kind of data to read and where to write. You have the execution kernels ready, they are created from program objects. And then the important thing is, as we are saying, that you don't really launch the commands, the runtime systems are going to launch the commands, but the order in which things would happen you can specify using the command queue, that well you read, write, execute, read, write, execute in this order, and when you execute those commands you can actually give instruction whether to execute them in order or whether to execute them out of order, like that. So, these are the different phases through which a typical OpenCL program's execution would go through. With this we will be ending this lecture. Thank you for your attention.